Hello, everybody. Over the next 15 minutes, I'm going to talk to you about some of our recent work at Lightwave Logic. The title of my talk is EO Polymer Modulator Platform with Enhanced Stability at both 1.3 microns and 1.5 microns. And let's go to the next slide. Safe harbor slide. The only thing I want to show from this slide is the gray bar at the bottom. So if there's too much technical data, you can just focus on the takeaway at the bottom of the slide. These slides will be posted on our website as well as the Market Focus website. So you can sit back and relax and you don't have to take lots of notes. The agenda today, I'm going to talk a little bit about the market environment, technology trends, some of the uniqueness of polymers and the work we've been doing. And then I'll wrap with a couple of the latest industry photonics roadmaps, which I typically show because I think that's really important for all of us in the community. And then I'll summarize. So in terms of the market environment, being able to market position yourself in a dynamic environment is very important. And so we're focused on our technology suite to address major pain points facing some of the network operators. And in this slide, you can see three colored boxes. The one on the left, engineering advantage, you've got to be able to have platform flexibility. And we certainly see that from our materials work. That leads into faster networks, that you've got to be able to enable faster networks and faster devices. And then you've got to look at where you can save energy into the network. We're trying to keep the power consumption down. So at the takeaway at the bottom of this slide, material science, which is what we do, goes into fast devices that are low power, gives you some design flexibility, gets you some more efficient networks, and then actually the impacts to lower energy costs. So let's take a quick look at the technology trends. Now, this is a slide that's entitled Industry is Driving Photonic Integrated Circuits, PICs. And I've shown some incumbent technologies on the left in red, indium phosphide, on the right, silicon photonics, and we'll hear more about that in the next talk. Some of the attributes from some of the devices you get into these platforms, you can see in the lower left-hand corner. I would argue that indium phosphide modulators have some limitations in speed. And certainly we know that from the electronics, you can't get GPUs or CPUs from indium phosphide, but you certainly can from silicon, which is on the lower right-hand side. I would also argue some of the speeds for the silicon modulator could be classed as limited. Certainly we've been focusing on our technology to try and address that. And so incumbent technologies, we believe, could use a boost from faster devices such as modulators. And so as an overlay from the previous slide, I've colored the center section in green, which is indicative of what we're calling polymers, Polymer Plus, making polymers additive to photonic integrated circuits. So the title of this slide is Hybrid Photonic Integrated Circuits, adding polymers to your platform, whether it's indium phosphide PIC or a silicon photonics PIC. And certainly a polymer modulator is very, very fast and very low power. And so the takeaway from this slide is with polymers, you should be able to upgrade your integrated photonics platform and achieve some faster speeds and lower powers. And so what is the uniqueness of this technology? Well, at the very highest level, EO S21 bandwidths of greater than 70 gigahertz. In fact, 100 gigahertz has been demonstrated. Lower power, so you can actually direct drive from CMOS, lower cost and robustness. And so upgrading your modulator platform, we feel is important. And certainly the work we've done in EO polymers supports that. And so in the meantime, we've put together a really strong patent portfolio. We've also included some of the BR photonics work that we acquired the assets a couple of years ago. And certainly we have a lot of IP in materials chemistry, optical devices, packaging, etc. What does that all mean? It means that you have some pretty good freedom of manufacturing to go off and add polymer technologies to a silicon photonics platform. And what really happens in this work? Well, you have to pull the chromophore and align them just like you do in LCDs. You know, some of the displays you find in TVs and mobile products, etc. And so applying a voltage aligns the dipoles. but also we're using polymers. And so that's also similar to the organic LEDs, which is also using polymer technologies. So we're actually sort of combining the pollen that gets used in LCDs and the polymer organic type of material that's used in organic LEDs, which you find in your phones and TVs today. But the way we use our polymers, our electro-optic polymers, is we actually form them into Mach-Zehnder modulators, as been seen from this slide. And you can see from the green arrow the optical data in, and you combine that with RF data, and you can get a combined output on the outside. And this is a polymer building block that switches light very, very fast at low voltage. And so one of the main assets is for using EO polymers is simple, low-cost fabrication. And the key here is that you want to have the fabrication equipment the same as what you normally use in any semiconductor fab. So no exotic equipment needed, standard photoliths and patenting. You'd be able to scale the wafers just like you do in semiconductors. And of course, if it's a simple process, you can minimize the cycle time. So this is what we've been focusing on. And in fact, you can see this is 3 different types of approaches for making polymer modulators. The one on the left is the traditional one, a polymer stack, where you have a core and 2 claddings, an upper and lower cladding. This is what folks have been working on for the last 20 years, traditional polymer stack modulator. This is the one we've been working on. We've actually started working on a new one. We put out a press release a couple of weeks ago on that. We call that Polymer Plus. You've been able to simplify the way you put polymers down onto an integrated silicon photonics platform. And that's what we're calling Polymer Plus. We have worked on polymer slots, and so have many other people. We're still continuing to work on polymer slots. The advantage of slots is that they're very, very small form factor. But today, you can see the red circle on this slide. We're focusing on the polymer stack and the Polymer Plus with integrated photonics platforms. And now this slide is a slide to try and just calibrate everybody. It's a spider competitive chart. And so the way these charts work is you have a diamond, and if you completely fill the diamond, then you've covered the 4 main metrics. You can see here, I've got high speed, stability, low power, and size as the metric. In terms of silicon photonics in blue, indium phosphide in green, lithium niobate in red. And then the polymers in sort of a goldy color. In the blue one, just to get everybody updated, there's been a lot of talk recently about silicon microresonators. I've added that in terms of a dotted line, a blue dotted line, to show that in silicon microresonators, even though they're going through advanced development today, they are very, very small in terms of size. They've got some good stability and they're fairly low power. And so we can compare that to the green indium phosphide and the lithium niobate. In terms of the polymers, we can see the very, very low power. The really small one is the polymer slot. But in general, the polymers can all operate at really high speed. And so we think adding polymers to any integrated photonics platform is attractive. And so some of our latest results, and this goes back to the title of this slide, historically, EO polymers have been working in the 1550 nanometers. And I don't know if there's any papers on 1310. If there are very, very few. But certainly this year, we showed some really nice performances of R33s of 1310 nanometer technology. So now our polymer platform is not only 1550, but actually can add the 1310 wavelength regime to it too. And that means from our standpoint, that's an important material building block and gives us a broader optical communications applications for high speed and low power. This slide here is a question that comes up lots and lots of times when you talk about polymers. Even though the OLEDs, organic LEDs, have been out for 10 years now, are very, very reliable, people still ask questions about how reliable and how stable the polymer materials are. Graph on the left shows R33 stability, 85 degrees in nitrogen, showing 4,000 hours, greater than 95% stable, which is really nice. The one in the middle is a really tough experiment. That's broadband light exposure. That's 13 milliwatts in an oxygen atmosphere. The reason why this is a tough test is because the output peak of the EO modulator polymer material is about 800 nanometers, and that overlaps with the absorption peak. And so that is an extreme test. And so we've actually improved our materials up to 95%, and we expect that to be much higher in the future. So we're really working on that middle graph. And the one on the right-hand side, you can see there's really good stability with 1310 light exposure to 100 milliwatts, greater than 99%. And so we're doing a lot of different various conditions and temperatures. And over the course of the next year, we'll be putting more data out to support these types of experiments. In terms of high-speed performance, I think it's pretty well known that EO modulators can work fairly well at analog bandwidths, EOS21s of 70 gigahertz. That equates to 100 gigabits per second using an NRZ format. Or if you want to use PAM4, you can double it up to 200 gigabaud. Because we do believe that the optical devices really need to support at least 100G, if not 200G data rates. So the last couple of slides, I'm going to show industry photonics roadmap. The good news is that the folks that put these roadmaps together, and I'm certainly one of the folks on the committee to do that, are looking at hybrid solutions for photonic integrated circuits that include both silicon photonics, indium phosphide, polymers, dielectrics, and even gallium arsenide. But in this one here, this was done, as you can see from the top left-hand corner, in 2016. And this is what was predicted to happen in 2020. And so the reason why I want to put the slides on our website, and you can look at the Market Focus website, is because there's a lot of data here. Don't expect everybody to read this data. But the next slide is most interesting. That's what we predicted. And it actually came out fairly true. We predicted by 2020, you'd see 400 gigabits per second, less than $5 per gigabit in terms of a metric. And so 50 gig per second speeds. And so this sort of happened. It was fairly accurate. So it was sort of surprising. And then in the last year, we've put a new roadmap together. This is this one in green. This is the 2020 roadmap, and you can see some of the metrics have been updated to look at what's going to happen in the next 3 or 4 years. And while some folks may disagree with this, certainly this is a living document, and these types of roadmaps can get updated all the time. And so where are we going? So let's take a look at some of the big trends we're going to see in the next 3 or 4 years. Certainly hybrid PICs is certainly going to be a big play. We're certainly going to see 800 gigabit per second modules. We're going to see folks trying to address how to get to 1600 and beyond. We're going to see metrics of $2 per gigabit per second. We're going to see faster devices. We're going to see low power. We're going to see athermal designs. So all these things are going to come into play. But I think the big takeaway here is, yes, there's going to be higher speed and lower cost, but it's going to be hybrid solutions. We're going to see people use different types of material technologies, packaging technologies, different co-packaging type solutions in order to achieve the goals for the system and the architectural network. And certainly high speed, low power is supporting of that into the hybrid PICs. So let me just go to the summary. And so I think polymers can deliver some radical innovation, especially from the modulator standpoint. So enabling lower power, faster, unique, and differentiated solutions to your integrated photonics platform. And the last slide I've got here is that, you know, what do we bring to the party? Certainly faster and lower power optical devices. We've actually added 1310 to the classic 1550 nanometer. So that means we have a broader application space. We've certainly, as a company, persisted when others really have abandoned this technology a long time ago. We certainly feel the time is right for polymers now. And we believe in terms of how we're positioning our polymer modulators to solving customer headaches, that they're additive to other integrated photonics platforms, and that's pretty innovative. And so we think these EO polymer modulators are ideal to upgrade your platform to get to 100 gigabits per second NRZ or 200 gigabaud PAM4 and etc. And for us and our standpoint, that's pretty exciting. Thank you very much.
Hey, thanks, Michael. So we have some questions from audience. The first question is, how close is this technology to commercialization? And also how you address the concerns for if you work on the telecom and the data area for the integration and the quality concerns.
So we have got prototypes, and so we're in the prototyping phase, especially for the polymer stack modulators, and we've been working on that for a number of years. And so we've demonstrated devices and results. And certainly we're talking to external folks about the performance of our devices, receiving feedback. And one of the things that I've focused on in this talk is the reliability and the stability, because that's the feedback we're getting from the external folks that we talk to about that. In terms of what was the second part of your question again, Frank? There was a
so
second
basically, because you work on the 1550, right, and 1310, right? That's telecom, kind of a telecom wavelengths. So how you address the integration and also the quality concerns? So from the, go ahead.
Yeah, so the best way to approach this is individual modulators that are packaged in gold boxes is really not going to play as we move forward. There is a big trend, both in telecom as well as datacom, to look at different types of integrated solutions, whether that integrated solution is an integrated chip, or it's an integrated package, or it's a chip on board. And so a lot of folks are trying to figure out how to innovatively package the technology. And so a gold box is certainly not the right vehicle as we look forward to the future. So we've got to be able to simplify what the polymer design is and actually make that additive to an integrated photonics platform. And that is really the right trend. That's what we're working on right now. But in terms of the classic 3-layer stack, yes, you can put that onto an integrated photonics platform, but we feel that we can make that a lot more simpler, lower cost using less layers, and that's why I indicated in that slide called Polymer Plus.
Okay, thank you, Mike. Another question regarding the performance from the thermal and also thermal stability or reliability comparisons. If you compare with the indium phosphide and also silicon photonics, because you talk about the hybrid integration. So how do you think it will gain tractions first, compare against the indium phosphide and silicon photonics modulators?
So classically, the silicon photonics and the indium phosphide modulator are semiconductor based, same as lithium niobate. So you're dealing with crystals. And so everybody knows that crystal technology over the last 30 years has proved itself out in terms of reliability and stability. Polymers is something that is, folks have done some nice work, even the BR Photonics and Gig Optics 10 years ago did nice telcordia work, did some really nice results there to show that the reliability and stability was great. But even after that work, people still ask a lot of questions. And we have to put this in perspective. We all are using polymers today for OLED-based televisions and even on our mobile phones and TVs. And so polymer technology is stable, it is reliable. What we have to do is we have to show the community that it is reliable and stable. And that's why we're focusing on the data right now, because in the end, it's the data that counts. And so that's where our focus is. And we are confident that once we show folks the data, it will just be accepted just like the crystal semiconductor technology.
Okay, thanks, Mark. One more question is for the higher speed. So currently, the IEEE start the beyond the 400G project. So we'll talk about 800G now. So currently, the CMOS electronics kind of have limitations for bandwidth and linearities. So consider the polymer modulators, how do you think the higher bandwidth optics will help?
Well, I think the whole ecosystem has to grow in speed and lower power consumption. And so, yes, I would agree with you that the ecosystem, a lot of the ICs are not that fast yet, but nothing's ever slowed them down. And so while we have a fast device, we also understand that the electronics also has to increase in speed too. But one of the bonuses of having a low power, low voltage modulator is that you can drive it directly from the CMOS. And so from a driving standpoint, there is some flexibility or ease, if you like. But in terms of the whole other infrastructure, what we're trying to promote here is a natural 100 gigabits per second ecosystem. And I certainly would like to see that. And that's why I'm really sort of excited about the high-speed devices.